Okay, so we just got this equation, right? So here you can make a correction. This is the fuel consumption rate per unit volume, but it's the average value over the flame. Okay, not as a function of x. Okay, now how do we get this equation? Okay. So what are the various symbols here? What is delta SC? That's the heat of combustion. Okay. And then here we have heat of combustion. So this is like the energy balance. Okay. So what is nu plus 1? So that's the mass of products, right? Because you take, let's say, 1 kilogram of fuel and then nu kilogram of oxidizer. So you have 1 plus nu. Let's say the nu value is 15, which is a typical value. So 1 kilogram of fuel, 15 kilogram of oxidizer, and then you get 16 kilogram of products. So 1 plus nu is the mass of products. Cp is constant, so it's also for the product. So you can see now what is this quantity. Okay. So the heat of combustion is used to heat up the products from this temperature Tu to Tb. Okay. So it's just thermal balance, energy balance. Nu will be in terms of kilogram, because then Cp will be, per kilogram.
Is it like gas fuel ratio?
Yeah, it's exactly that. Yeah, by mass. Yeah, air fuel ratio. Which is typical value is about 15. Yeah, you can see that because what is the units for Cp? It's like joules per kilogram per degree Kelvin. So degree Kelvin cancel and then kilogram will cancel.
Delta Fc will be in terms of kilojoules.
Yeah, delta S will be kilojoules. Because here you have reaction rate, okay, which is kilogram per meter cube per unit time. Okay. And then delta SC is joules. Okay. And then here you have, so this gives you per unit area, because this is per unit volume, and you multiply by a length, so that gives you, so everything is per unit area here, because this is mass flow rate per unit area. Okay. So anyway, so we got this equation, and this is just from the thermal energy balance. Okay. Now to get this equation, there is some analysis involved, so I'll just show you a couple of steps. So again, we look at the energy equation. Okay, now we integrate this equation from minus infinity to, like, in the flame, let's call it delta over 2. Okay. So again you have the mass flux Cp, and then we integrate this dt dx from minus infinity to delta over 2. Okay. Times dx. Okay. So now we also make this assumption that this is the flame thickness. So this is the thermal thickness, and then this is the reaction thickness. Okay. So from minus infinity, okay, up to delta over 2, the reaction rate is 0. Okay. So anyway, this quantity this term will be T at delta over 2 minus Tu, correct? Okay. Now, Spalding used a very drastic assumption that the temperature varies linearly. Okay. So, objective was to get an analytical solution, theoretical values. So, if it is a linear variation, then this is equal to Tb minus Tu plus Tu divided by 2. Okay. If the temperature varies linearly. Okay. And then the next term, if you integrate, it will give us minus lambda dt dx from minus infinity to delta over 2. Okay. So, at minus infinity again it is 0, okay. But at delta over 2, okay, lambda is a constant. So, what is dt dx? Okay. The model we are using, linear variation. So, dt dx will be divided by delta. Okay. So this is done, and this one is 0. We assume that the reaction rate from minus infinity to delta over 2 is 0. Okay. So we get a simple equation for the temperature. So if you plug this value, so this will be this quantity, this minus this, so minus lambda Tb minus Tu over delta. So only thing left is we plug this value where we did already, so nothing is left. Okay. So I will write the final equation, what you get from this. So this is in the notes here. It's not in the printed notes, I just wrote it over. Okay, so you use this equation. We already got this equation, and this will give us another equation. Okay. So basically, then we have two equations for delta and SL. Okay, and of course we use this for delta SC. Okay. Delta SC can be replaced here by this quantity. So using those two equations, one this one and then one coming from here, you just plug in everything. So then you'll end up with this equation, okay, for the flame speed. And similarly, you'll get an equation for delta. Okay. Any questions? Okay. So this I find useful because you're actually looking at the flame. Of course, you're making very drastic assumption, but it gives you a lot of physics. Like what is delta SC? Where is delta SC used? So again, we remember what the model we are using. 3 species, all the transport properties are constant, temperature varies linearly, half of the flame reactions are 0. Okay, there are a lot of assumptions involved. Okay. But now let's compare the results. So now we get a flame speed, okay, which includes the effect of fuel aeration. Okay. If we go back, so this is an improved result over this. Okay. Here we just had omega dot reaction rate alpha divided by rho u. Oh, going back, sorry. Now we are getting, okay, instead of omega dot we are writing, this is same as omega dot, reaction rate, okay, divided by rho u alpha. So those were, parameters are still here. In addition, we are getting this 2 times nu plus 1. Okay. And any question about this minus sign? Because this is negative. The reaction rate of fuel, okay, is negative. So this is the rate of consumption of fuel per unit volume. Okay. And this equation was just alpha over SL. So now we are getting a, the constant factor, so which comes out to be 2. Okay. And remember, this fuel consumption rate is the average over the flame. Okay. So anyway, these quantities are defined. Nu is the stoichiometric fuel air ratio. Actually, we use this even if it is not stoichiometric value. Okay. So you are given, let's say, certain amount of fuel and certain amount of air, then you can calculate what is the value of nu. So it doesn't have to be exactly stoichiometric. Okay. And we use these equations, these two equations, to look at the effect of various parameters on the flame speed and flame thickness. For example, effect of pressure, equivalence ratio, effect of temperature, effect of fuel, different effects we can consider by using these two equations. So we did the scale analysis, dimension analysis, and then this is a more refined analysis based on the actual conservation equation. And to get the solution, of course, we have to simplify those equations, a lot. Okay. But we do get a solution. Okay, to do more detailed analysis, we have to depend on the numerical methods. Okay. And there is actually more detailed analysis without the numerical also. So I have given you some references here. You can look at this. One-dimensional premix flame in Coe's book. Okay. And then they're also using Chemkin. So within Chemkin, Chemkin is like a suite of softwares. It's not just one software. You can do equilibrium calculation. You can do, premix flames, diffusion flame. So then you use, different options in the software. So for premix flames, you use this option premix within the software. So then it will activate the premix module in that software. So both Turn's book and Coe's book, they explain, how to use and get the premix flames using premix module in Chemkin. Okay. You can also use the counterflow. You can do the counterflow premix flame calculations. Then in Chemkin, you use the module is opdiff. That's for the counterflow configuration. Okay. I showed you some results earlier. Those were using this option. Okay. I can show you that again. It's right here. This flame. Okay. So you can do one-dimensional flame like freely propagating flame like in a tube. Okay. In a tube, if you do, then the flow velocity at the entrance of the tube will give you the flame speed. Okay. You can also do burner stabilized flame, like if you have a tube and you have a flame right at the exit of the tube, which are like flat flames, or you can do counterflow flame. Okay. So there are 3 different configurations you can use for computation of these laminar premix flames. Okay. Now we won't have time to go through there's last 15-20 years there have been many advancements in the understanding of this laminar flames, and then this is also a bridge to turbulent flames. Okay. And also there are other related phenomena like effect of flame stretch, effect of flame stretch on flame speed, on flame stability, and also the effect of Lewis number. Okay. So that we have to leave it out for more advanced course. Okay, I mentioned here using Chemkin. So if you do freely propagating flames, then the equations are same we have already discussed. Okay. So this is the mixture mass conservation, that is rho times V is constant. Then the species equation, the convective term, the diffusive term, and then the reaction term. Okay. Pressure is constant. So this becomes your momentum equation. dP dx is 0. Okay. And then the energy equation in terms of temperature. Now here we have the species diffusion term. Okay. So this is the conduction. This is the diffusion of heat due to species diffusion. Okay, and then of course is the rate of heat release due to chemical reaction. Okay. So you solve these equations together using these boundary conditions. Okay, at infinity T is Tu. What is Yi? Yes. So you specify what is your mixture. Okay. What is the equivalence ratio? Then you know what is the mass fraction of fuel, mass fraction of O2, mass fraction of nitrogen. So now you don't have to assume just 3 species. You can do detailed calculation. Okay. So these are the conditions at minus infinity. And then at plus infinity, you have dt dx 0 and dy dx is equal to 0. Okay. And for solving these equations, these are of course the unknowns. You have the standard unknowns, density. This is now velocity as a function of x. In Microsoft Word, that's how the small v looks like. You all know. Okay. So that's the velocity as a function of x. So all these properties except SL, okay, are functions of x. So that gives you the flame structure, because you can plot Yi, any species you can plot in the flame. Okay. If fuel, oxygen, nitrogen, whatever fuel, then CO2. I'll show you some results. And you also get the flame speed. Okay. So now you get more accurate values and you can compare with your experimental data. Okay. So you can validate your experimental data also if you do some new measurements. And people have used this approach, very extensively to look at different fuels. You can also use this to validate your reaction mechanisms, because you can compare your flame speed and flame structure to the experimental data and see which mechanism works better for you. Okay. So now what you need for doing this, if you use this software, remember you need 3 files other than the software. Okay. So remember what are those 3 files? The kinetic, the reaction mechanism file, then the thermo file and transport files. Okay. So you will need all those files. Okay. And of course, in addition to these equations, you have the ideal gas equation, which is actually used to calculate density. This equation is used to calculate velocity. Okay. And so we should know that this flame speed is an eigenvalue. That means the solution will be good, for particular value of the flow velocity at the entrance. Okay. So that's the eigenvalue of the problem. Okay, so the flame speed is part of your solution. So this is some results. This is for a propane flame. So I'm plotting here flame speed versus equivalence ratio. Okay. You have the experimental data. Okay. And of course, this is doing Chemkin computation, Chemkin software. Now this was a student project, so it's not like students spend the like lot of time to get really good match by changing numerical parameters. Okay. He did best he could do for a project. Okay. So this was like a class one of the two projects. So for atmospheric conditions, you can get for 1 atmosphere you can get even better match, but this is pretty reasonable match with the experimental data. Then you have the flame structure. So this is propane air flame at equivalence ratio 1. Okay. So this is the flame speed at different equivalence ratio. Okay. So for equivalence ratio 1, we plotted the flame structure. Okay. So you can plot at other equivalence ratios if once you get the solution. So axial velocity, which one is the axial velocity? The symbol is missing.
Black color.
I think the black color is axial velocity. Yeah, there is an arrow here. Okay. So this velocity here, okay, gives the flame speed. It's not exactly at 0. Okay. So this is near the flame, 4.9 centimeter from the entrance. Okay. And you can see how the flame thickness is. To get the flame thickness, the reaction zone, you can plot the heat release rate. Okay. So that's the heat release rate. You can also plot the reaction rates for different species if you want. So it gives you a lot of tools to analyze this in detail, a lot of data to analyze. So heat release rate is the blue line, and then temperature. So you see the velocity almost follows the temperature. Temperature increases by a factor of 7. Velocity also increases. So velocity here is about 40, 35, 40, and then here it's like 3 meters. Okay, 300 centimeters. Temperature is close to the adiabatic flame temperature. It may not be exactly adiabatic because you may have like CO and H2. And then you can look at the detailed chemical structure of the flame. Oxygen, propane, okay, and then H2O, CO2. Again, you can see the H2O starts forming earlier compared to CO2. And then H2. So when you analyze these premixed flames or even diffusion flames, so these are the major species you plot. Okay. So you can see that the CO starts forming, and then the CO2 starts a little bit later. Okay. Then CO peaks here, so then CO2 keeps forming more. Okay. And then of course these values decrease, CO and H2. Okay. Then you can also analyze the intermediate hydrocarbons. Okay. So this is the fuel mole mass fraction, or mole fraction rather. Okay. This is just used to indicate where the flame is, and then you can see this for propane C2H6, CH4, C2H2. These are just some of the intermediate hydrocarbons. So they are produced and then they are consumed. Okay. And it depends, if you want to do more detailed analysis of the reaction mechanism, then you can look at in detail, where is this produced compared to the other species. Okay, it gives you, it's like a reactor now. Remember yesterday I was showing you some, yesterday or day before, like a yesterday, you know, the all these species, you know, mole fraction in a reactor. So flame is also a reactor. Okay. So this is showing, you know, the intermediate species.
So what is the shape of this reactor, sir?
No, shape is the one dimension. It's like flame is the reactor. It's not the reactor. Saying, you know, flame itself is like a reactor because you feed it this fuel and you get products. And you get products at high temperature. Okay. Any questions?
So what is the thickness of the flame?
Well, we can compute that or estimate it. So you can say from roughly from 4.95 to, or you can say this is like the thickness of the flame. Okay. You know, if you want to get more precise value, you can look at the reaction rate profile, or you can look at, you know, OH value. But this is a pretty good estimate. It's about 2 millimeter for this case. So very, very small, you know, thickness. Okay. Because if you look at the mole fraction of fuel, I did not plot right from the beginning. Here it is like 0.04 already. So at the entrance, obviously it was a little higher than this value. It's not 0.04. So some fuel is being consumed, but at a very slow rate. Then it becomes very fast here. As the fuel is consumed, you are forming the C2H6, C2H4. Plotting only some of the species. You have lots of species in this. Here we use the detailed mechanism is, you know, this has been reported by people at, you know, University of Southern California. Okay. So if you are interested in propane flames, this mechanism will work for methane, propane, and also syngas, up to C3 species. Okay. Also ethane, that means acetylene. Okay. So C1, C2, C3, okay, it gives reasonable results, especially for atmosphere. Even for higher pressure, it, you know, we have done that, it gives, you know, reasonable results. So University of Southern, there are other mechanisms, just say propane mechanisms. You can download, you know, few others. Yeah.
Which species are responsible for
Soot
soot formation?
formation for propane, okay, here it will be C2H2. Yeah. Yeah, acetylene. Okay. If you use more detailed chemistry, you can also use, you know, benzene, but then it depends on the reaction mechanism. So a lot of mechanisms do not contain, you know, aromatic species. So then you have to use more detailed mechanism if you want to look at benzene. Benzene actually gives a better value for the, you know, soot concentration. But acetylene is also a good precursor for soot.
Sir, these combustion results are available at the
This slide is available, I think, in the,
at high pressure it's available,
at high pressure.
like a 15-20 watt.
Oh, I don't know whether we did because this was a class project. Okay. But if there is some interest, you know, we can do at different pressures, you know. Okay, so we now, let's summarize. So we have done the dimensional analysis and then the thermal analysis, you know, based on the thermal theory, you know, reported by Spalding. Okay, then there are some more detailed analysis in the textbooks you can find. Okay, like Coe's book, Foreman Williams book, most of that textbook, they have some more detailed analysis. And then the analysis based on the software. So these are the, because there's summary 4 approaches we have discussed. Because more detailed analysis based on theory, we did not do that. But you can find that in these books. Okay. So now, the rest of the lecture today will spend on looking at the effect of various parameters, on the flame speed and flame thickness. So just qualitative results, and of course I'll match, support these results with the data from the literature. Okay. So again, this is based on fuel, nu times air gives you products. Okay. And these are the equations now for the flame speed and flame thickness. So to understand the effect of other parameters, you just write what is reaction rate, okay, and then we can discuss what is the effect. Okay. So let's look at this fuel consumption rate. Okay. So let's see if it makes sense to you, all of you. Okay. So what is A times this exponential? That's the reaction rate constant. Okay. And then this is the mole, this is the concentration of fuel, and this is like some difference here. This is the concentration of oxygen, not air. Okay. This is air here. And these powers are from experimental data. Okay. So this is a global one-step mechanism. Okay. Now to see the effect of pressure and temperature, we use this equation. The concentration is.
Sir, whether the A and B are stoichiometric coefficients, sir?
Oh no,
After
these
the
are.
chemical reaction?
No, these are just based on the some experimental data for reaction rate. So they match this equation with the experimental data. Typical value like A is like -1, -0.1, -0.2. So minus also doesn't make any sense. So it's totally based on so it's an empirical equation. And B is like 1.5 or 1.6. Okay. You can find in these books also what values. But theoretically, if you use stoichiometric values, this will be 1 and 1 then. Because two body reaction is a second order reaction. So then A plus B should be equal to 2. Okay. But I'll show results to you here. I'll show that this A plus B can vary a lot with the pressure and other conditions. Okay. Anyway, so use this equation and then replace this concentration by mass fraction. Okay. Because concentration is, if you multiply by m, what is then concentration times m? Concentration is number of moles per unit volume. You multiply by molecular weight, mass per unit volume, which is rho times y. Okay. This is written for any species. There should be rho times yi, right? Okay. And then pressure, the density is, okay, that's the equation of state. So it's not exactly we are writing, we are just looking at what is the variation with other parameters. Okay. So density will go like pressure molecular weight divided by temperature. So I'm not writing like gas constant there. Okay. Because you just want to see what is the effect qualitatively. Okay, so substitute this equation, these two, into the reaction rate, and you see this reaction rate. So what we see here is reaction rate divided by rho u. So we're writing the equation for this ratio, from here. Okay. So now this also contains alpha. So alpha also depends on temperature and pressure. So without going into a lot of details, alpha typically is, so here, in this book, this is based on Turn's book, they have split this into unburned temperature and some average temperature, because the temperature varies a lot in the flame. Okay. So basically you can take C equal to 0.5. Okay. So alpha varies as temperature to the power 3 half, 1.5. Okay. Then 1.5 they split into two different temperatures. Okay. TU, and then average temperature will be TU plus TB divided by 2. Okay. So you substitute for alpha here, and this quantity WF dot divided by rho u into this equation, and then you get this. Okay. So it's a very simple qualitative analysis. Okay. So C is 0.5, then you can see this is like, okay, very weak variation, 0.25. Okay. TU is important, right? It shows you what is the effect of, okay, reactant temperature on the flame speed. Okay. What is TB? That's the adiabatic flame temperature, right, roughly. Okay. And then again here you have TB, okay, exponential term. So the biggest effect adiabatic flame temperature is in this term because of the exponential factor. This has a small effect, okay, compared to this term. Okay. And then pressure effect is n minus 2 divided by 2. What is n? N is A plus B. Okay. So people normally take n equal to 2, second order reaction. Okay. But the results show that this n varies a lot, if you change the pressure, it's not always 2. And then if you substitute this SL in this equation on alpha from here, you can also write the effect on the flame thickness. Okay. And typically what you see, whatever say increases the flame speed, it decreases the flame thickness. Okay. You can see from here also, it's not universally proportional to flame speed. Okay. So at equivalence ratio near 1, flame speed is maximum, right? Then the flame thickness will be minimum. Okay.
So for n equal to 2, the
Yeah.
flame speed is independent of pressure.
Yeah, that's an interesting result. Flame speed is independent. There is some discussion on the next slide why. Okay. But actually it's not correct. Okay. It becomes, if n is 2, it does become independent of pressure. Okay. But n is not 2, okay, most of the time. So that is discussed here. So n is the global reaction order, okay, A plus B. So it is often assumed as 2, which implies that both SL become independent of pressure, and delta then decreases with pressure, from this equation. When n is 2, this will be 1 over P. Okay. So now n is 2, that means the reaction rate varies as p square, right? Okay. Then SL should be, okay. Then SL is, independent of pressure, 0 means, okay. And this is just what happens is if you increase pressure, alpha increases. So here alpha increases, but density also increases, okay. Okay. So this is what is written here. So note that the reaction rate increases with pressure because this is I think P1, sorry, not P0. This is P1. Okay. Sorry? No, P1, P to the power 1. It's P. Yeah, because P square, so SL will be because
2 minus 2 by 2 is 0.
no, the reaction rate here is P square. Okay. Whereas alpha is 1 over P. Okay. So basically what it means is the flame speed is, okay. Yeah, because the reaction rate increases with pressure, but the mixture has no more mass because density increases. Okay. So the reaction rate is increasing, but you have to burn more mass at higher pressure, right? Okay. So they balance out. You're burning more mass, but it's burning faster. Okay. Again, remember, actually, I don't remember who asked me, the flame speed is also called the burning rate. Yeah, you asked me, okay. So it's also called the laminar burning rate. Okay. Sometimes they use burning rate as flame speed times the density. Then it's the mass burning rate per unit area. Okay. So many people prefer to use, mass burning rate compared to the flame speed in their analysis. Okay. The effect of P on the flame speed flame thickness is mainly that the P increases the reaction rate, so flame thickness will decrease. Okay. Now, the actual data, if you look at, it shows that N is very complex. It has a complex variation with pressure. Okay. So the reaction order varies with pressure due to chemical effects. Remember we discussed the wall effects at low pressures. Okay. And then three-body reactions become important at high pressures. So the reaction order can change a lot with pressure. Okay. And the flame temperature can also vary somewhat with pressure. Okay. We looked at the chemical composition and remember there was some effect of pressure. So that can also change the flame temperature. Okay. So there are some graphs here showing the effect of this is the graph. So this is from my student, Shubhendu Som, who did masters, and then he continued to do PhD. So this was his master's work. So he looked at this methane air flames. This was part of his work. He did some other stuff also. So laminar flame speed. This was done using ChemCane, and then there are different, 4 different mechanisms for methane air mixtures. We checked 3, 2.11. So this is almost like 10 years back. And then San Diego mechanism. This mechanism is, you can also download this mechanism. Go to San Diego mechanism, you can find that. Okay. This is maintained by University of San Diego, University of California, San Diego. The 2 professors there, Asha Chaudhary and Foreman Williams. Okay, so they maintain this mechanism. This also works for several fuels. Okay. And then we had another mechanism called C2 mechanism, which was a simplified version of GRI mechanism. Okay. So they all give similar behavior, these mechanisms, okay, for methane airframes, and it matches also reasonably well with the experimental data. Data was only up to 20 atmosphere. Okay. So what interesting result he got, okay, that he can extract the reaction order from these results. Okay. So the actual reaction order, because he can calculate the reaction rate at different pressures, so there you can get the reaction order. Okay. So you see how much it varies with pressure. As you increase pressure, it starts like 1.5, then it decreases a lot first. Okay. And then it starts increasing at some like pressure about 5-6 atmosphere. Okay. Only at very high pressure, reaction order is becoming, what is the value? About 2. So when the reaction order becomes about 2, then the flame speed becomes almost independent of pressure. So this is only observed at very high pressure, that the flame speed is independent of pressure. At moderate pressure, it decreases a lot with pressure. That's the effect which can be observed for all kinds of fuels, not just methane. So this is a typical behavior of the effect of pressure on flame speed. Okay, that it decreases rapidly. We start from 1 atmosphere, and then it kind of levels off. Okay, at high pressure. Okay, any questions? Oh, that was the title, which I didn't remember. Then there are some other results. This is now flame speed versus equivalence ratio. Okay. So let's now discuss, why it should vary with equivalence ratio. This is for heptane air mixtures, then this was a few years back. Okay. So this student his research was not just flame speed. This is just to show that the mechanism we are using is okay to use for other, research. So he was doing partially premixed flames and he was doing emissions, but first he has to show he has to validate the mechanism he was using. He validate is using, the experimental data of Davison law. So now let's discuss, okay, why should show a peak here near equivalence ratio 1? Okay, now you remember, like, how does the adiabatic flame temperature vary with equivalence ratio?
Like increase slash.
Yeah, it's similar to this, which is a plot, right? If you plot the adiabatic flame temperature. So now, if you go back, here, or rather here, see the flame speed. This is the effect on the adiabatic flame temperature. This is the effect of adiabatic flame temperature. Okay. So this has the maximum effect on the flame speed, like this TB, because of the exponential term. Okay. So whichever way the adiabatic flame temperature behave, flame speed will follow that. Okay. Then of course you also have some effect here, but that's a small effect. Mostly the effect of equivalence ratio comes through adiabatic flame temperature. Okay. So you cannot see directly the effect of equivalence ratio. So it comes through the adiabatic flame temperature. Okay. So both TU and TB have strong influence on SL. Okay. Because if you increase the initial temperature, what happens to the adiabatic flame temperature? That will also increase. If you go, the adiabatic flame temperature is 2000, and your unburned mixture temperature from 300 to 600, then your adiabatic flame temperature will also increase by 300. So that will increase the flame speed. Okay. So the reactant temperature has a strong effect on the flame speed, and there is a lot of data in the literature you can find. Okay, effect of TU. Yeah, this is like the very rough equation. TB TU plus delta SC over CP. Okay. So this directly tells you the effect of unburnt mixture temperature. Okay. And as we indicated is all just now, effect of TB, this is like the adiabatic flame temperature. This comes through the exponential term. Okay. So this is the effect equivalence, and this is again a very typical behavior. How does the flame speed vary with the equivalence ratio? And you can also note the value. Okay, about 40 centimeter. Okay, methane is also about the same value at 1 atmosphere, about 40 centimeters. These are for other fuels. So this is for hydrogen air mixtures. Okay. So for hydrogen air mixtures, the peak value is around phi equal to 2. Okay, not near 1. The stoichiometric value will still be near 1, but equivalence ratio is about 2, where you get the maximum flame speed. Okay. So any gas, why it's at a higher equivalence ratio for hydrogen. So this is a unique for hydrogen. Okay. This is due to the diffusivity of hydrogen, because you have more hydrogen. Okay. Then hydrogen can diffuse much faster and then react. So that's why at higher it goes to higher equivalence ratio, because there is more hydrogen. Okay. So this is the transport effect. So here, this is from another student's thesis. So he compared with using GRI and then another mechanism for hydrogen, Mueller mechanism, and then 3 sets of experimental data. So you can see that there are variation within the experimental data also. Okay. So there's nothing like exact values. Okay. So this is the effect of pressure. So flame speed is now plotted versus equivalence ratio at different pressures. Okay. So one is shown here. Okay. So this is about 300. Then at 5 atmosphere, it's actually a little bit higher. Okay. And then it decreases a lot. So this is again unique with the hydrogen that can increase also with pressure. Okay. I think this was, we were not really interested in helium. This is because the experimental data was for this mixture. Okay.
It's a diluent.
Yeah, it's used as a diluent. I'll show some results of using diluent. But when you compare with experiment data, you have to use the same conditions. Okay. But If you want to look at that, this is, okay, Say et al. I think this was, he is now a professor. This was his student work, I don't remember where, maybe Princeton, but now he's a professor at Rutgers University. So actually, he sent us the data. He sent the data to my student. I think he was working with the CK Law, either as a postdoc or as a student. I don't remember when he produced the data. Yeah, CK Law, they have this setup. Okay, it's like a constant volume type of reactor, maybe constant pressure. I don't remember, but there is a fuel air mixture, and you ignite in the center of the reactor, and a spherical flame then propagates out. So then taking a lot of pictures, they can get the flame speed as this flame expands, and it propagates out radially. Okay, and then they can extract the flame speed. So that's what this experimental data is. Yeah.
So why so much high flame speeds compared to other things?
Yeah, this is again for hydrogen only. For hydrogen, the flame speed is much higher. Okay. Again, for this, we can go back to this result, this equation. So the reaction rate is very high for hydrogen air mixtures, okay, compared to hydrocarbons. See, hydrocarbons have to go through several steps before you produce radicals. So for hydrogen air mixtures, hydrogen, oxygen, they react and they produce OH. That is enough to initiate the reaction. And then right away H, O and OH are formed. So reaction rates are much higher. Other thing is alpha. Density is low. What about alpha? Alpha means the mass diffusivity is much higher. Alpha is not, but mass diffusivity is higher. Well, thermal diffusivity, I don't know whether it's that much different from methane, but alpha definitely, the mass diffusivity definitely is much higher. Okay. So it's the diffusion effect, reaction effect on reaction rate, and also density. Okay. Oh, here also I should mention something. Yeah, typically flame speed and flame thickness are maximum and minimum near stoichiometric for hydrocarbon flames. For hydrogen, it is at a richer mixture, equivalence ratio, about 2. If the pressure is different, it can be at a different equivalence ratio.
Syngas.
I think I may have it here, but we have done syngas. And there are a lot of data also. Let me see if I may have some syngas graph.
Sir, in the above plots, whether you are maintaining temperature constant, sir? Just
The reactant temperature?
no, sir. Yes, sir, the reactant.
Yeah.
You are maintaining the temperature as constant,
Yeah, it's-
increasing the pressure.
Yeah, exactly. Yeah, 300 degree Kelvin or 298, and then increase the pressure. Yeah. Yeah, when you use Chemkin, these you provide as initial conditions. Okay, the initial properties. Just like you provide equivalence ratio. Okay. Now this is a typical result for, this is taken from the book. Okay, flame thickness versus equivalence ratio. Okay. Now, this quenching distance, either we'll discuss this afternoon or tomorrow, depending how fast we go today. Okay. So, this is, okay, this quenching distance, okay, relates to the, if you have a flame propagating in a tube, okay, and then you decrease the thickness of the diameter of the tube, okay, the flame speed will decrease because of the heat loss to the wall. So far what we have discussed is all adiabatic conditions. There is no heat loss to the wall. Okay. So if there is a heat loss to the wall, then the reaction rates will decrease, flame temperature will decrease, and then the flame speed will decrease. So there is a minimum tube diameter which will sustain a premix flame. So if you go below that, flame will extinguish. Okay. So that's the minimum quenching distance. Okay. So that is also used, one of the important properties when you want to have a stable flame. Okay. So what you do is, you have a flame like a Bunsen burner flame. Okay. And then you decrease the flow velocity, right? So what will happen if you keep decreasing the flow velocity? It will be a flashback. Flame will go inside the tube. Now what you do is you keep decreasing the tube diameter. Okay. So eventually, you'll get to a small tube diameter where the flame will flash back, but it will get extinguished right away. It will not go to your tank. Okay. So that quenching diameter is very important for that, for safety. So what this shows is, it behaves almost like equivalence ratio, but it's higher than the flame thickness.
Diameter should always keep below 2 mm.
Sorry?
If you are keeping diameter of the tube below 2 mm, then there are not many.
Oh yeah, exactly. Yeah.
For most of the fluids. So this is for mechanical.
Yeah, you have to focus on the minimum value, right? Because your operating condition may be near equivalence ratio 1. Yeah, so that's about 2 millimeter here. Yeah. For methane air flames.
This is for premix flame.
Yeah. This is a very old data, 1972 from Combustion Institute. So this is the reference in the book. Okay, so I took directly this, copied from the book.
So for that, suppose you are having higher mass flow, right? So we can provide many less than 2 mm.
Yeah, they don't use just the minimum tube diameter. They actually use the quenching distance to design what they call the flame arrestor, to arrest the flame, to quench the flame. Okay. They use like a wire mesh. Okay. Okay, here is syngas results. You were asking me what. Yeah, this is also from the thesis of Shibendu Som. So this was published a few years back. So this is again, we were using this mechanism. Okay. So we are calling it Davis mechanism. Okay. So at University of Southern California, they had, first mechanism which they call USC 1 now. The latest one is USC 2. So this was the earlier version of the same mechanism. And then we also use, GRI 3. Okay. And then another mechanism, Mueller. So Mueller mechanism did not give good results. Okay. But GRI 3 and Davis gave probably the best results, but GRI 3 also, reasonable results. So this is showing the flame speed. So for two different syngas mixtures, 50% CO, 50% hydrogen, and then 95% CO, so 5%. So when you only 5% hydrogen, the flame speed decreases. Okay. So again, you can see for hydrogen it is much higher. So for 50%, it goes from 60 centimeter to 200 centimeters. This shows the effect of composition. So this is at equivalence ratio 2. So fixed equivalence ratio, you just vary the amount of CO versus hydrogen in syngas. So 0 means it's all hydrogen. Okay. And then it's all, so you cannot go to 100% CO because then you don't get any flame. Okay. So you have to have a very small amount of hydrogen. Okay, remember the mechanism we discussed for CO? You need either moisture or some hydrogen to initiate the reactions. Okay. So you can see it almost varies, inversely proportional to the amount of CO. It goes from 220, okay, to whatever the 25 or 30 centimeters. I think we can stop here.
Sir, so all this mechanism for a particular air fuel, it is giving better result, like other mechanism for some other methane air like that. Like this one is Davis et al. Is giving for the syngas good result.
Yeah.
Matching with experimental value.
Exactly. Yeah, so there are a lot of variation, So here we cannot say that, okay, GRI will give you good results always. A lot of people use GRI also for syngas. Now here we were studying the partially premixed flames with syngas. So this was again done for validation of the mechanism. So we used this Davis mechanism for the research part. Any other questions? Because I'll otherwise stop here.